The last talk today is by Professor Salvatore, that will talk about identities in group algebras, enveloping algebras, and related structures. Please, Professor.
Thank you, and thanks to the organizer for their kind invitation. The aim of my talk is to provide an overview of the main results about polynomial identities of group algebras, enveloping algebras, and some related structures like smash products and symmetric Poisson algebras, with special attention to the Lie identities satisfied by these algebras. I recall that an associative algebra A is said to satisfy a polynomial identity if there is a non-zero element in the free associative algebra of countable rank that vanishes under any substitution in A. We will say that A is resolvable, bounded triangle, or linear potent if A has the corresponding property when regarded as a Lie algebra via the usual bracket x, y, defined by xy minus yx for any x and y in A. Necessary and sufficient conditions under which a group algebra satisfies a polynomial identity were provided by Poisson in 1972. We will say that a group G is P abelian if P is a prime and the commutator subgroup of G is a finite P group. And in order to have a consistent terminology also in characteristic 0, by a zero abelian group will just mean an abelian group. Poisson showed that given a group G and a field F, the group algebra Fg satisfies a non-trivial polynomial identity if and only if G has a P abelian subgroup of a finite index. Next, the identities of group algebras have been extensively investigated by several authors. In particular, in the next theorem, Passy, Passman, and Segal characterized Lie nilpotency and Lie solvability. They proved that if G is a group and F a field, then the group algebra Fg is nilpotent if and only if G is P abelian and nilpotent, and Fg is resolvable if and only if either the characteristic of the ground field is different from 2 and G is P abelian, or the characteristic is 2 and G contains 2 abelian subgroup of index at most 2. Furthermore, Segal showed that the group algebra Fg is a bounded triangle if and only if either G is abelian or the characteristic is positive, G is nilpotent, and has a normal P abelian subgroup A such that G modulo A is a finite P group. Now we consider restricted and ordinary enveloping algebras. The characterization of restricted enveloping algebras satisfying a polynomial identity was obtained by Passman and independently by Petrogradsky in 1990. They showed that if L is a restricted Lie algebra over a field of positive characteristic P, then its restricted developing algebra satisfies a polynomial identity if and only if L contains restricted ideals A and B such that the following conditions are verified. Subsequently, by using this result as a starting point, Raleigh and Chalep became a systematic study of the Lie identities of a restrict enveloping algebra by establishing in particular when U of L is linear potent, bounded angle, or resolvable in odd characteristic. Precisely, they showed that given the restricted algebra L, its restricted enveloping algebra is linear potent if and only if L is linear potent and its derived subalgebra is finite dimensional and linear potent. Moreover, U of L is bounded angle if and only if L is nilpotent, L prime is p-nilpotent, and L contains a restricted ideal I such that L modulo I and I prime are both finite dimensional. Finally, under the assumption that the ground field has characteristic different from 2, the same authors proved that U of L is resolvable if and only if the derived subalgebra of L is finite dimensional and p-nilpotent. The solubility problem in characteristic 2 is much more involved and has been settled 20 years later, the result of Raleigh and Chalais, in a joint paper in collaboration with Hamid Hussein. We showed that if the restricted algebra is defined over a field of characteristic 2, then U of L is resolvable if and only if, after extending the scalars to the algebraic closure of the ground field, L contains a finite dimensional to nilpotent restricted ideal I such that L modulo I satisfies one of the following 5 conditions. Now, let's see the ordinary case. In 1963, Ladyshev showed that in characteristic 0, the ordinary enveloping algebra of the algebra L satisfies a polynomial identity if and only if L is abelian. Some years later, Yuri Bakhturin completed the classification by dealing with the prime characteristic case. He showed that capital U of L satisfies a polynomial identity if and only if L contains an abelian ideal of finite dimension and all inner derivations of L are algebraic of bounded degree. Now, it's known by a theorem by Raleigh and Chalais that in characteristic different from 2, an ordinary enveloping algebra is resolvable if and only if the algebra L is abelian. This is false in characteristic 2, as a 3-dimensional Heisenberg algebra already shows. However, by using our result for the restricted case, necessary and sufficient conditions on L such that capital U of L is resolvable can be obtained, thereby completing the classification also in the ordinary case. In fact, take L algebra L, defined over a field of characteristic 2, and suppose that its universal enveloping algebra is resolvable. Consider the restricted algebra consisting of all primitive elements of algebra capital U of L. Then L hat is the so-called minimal p-envelope of L, and one has that the ordinary enveloping algebra of L is isomorphic to the restricted enveloping algebra of L hat. And so our previous result applies. The conclusion is that given an arbitrary algebra L, its universal enveloping algebra is resolvable if and only if L is abelian or the characteristic of the ground field is 2 and one of the following conditions hold. So we have a complete answer also in the ordinary case. Now we will generalize simultaneously some results about group algebras and enveloping algebras by considering smash products. Let me first recall the definition and some basic facts. Given an off algebra H and a left H module algebra A, the smash product of A and H is the associative algebra having A tensor H as an underlying vector space and multiplication defined by the following formula. Now, if G is a group acting by automorphisms on an associative algebra A, then this action can be extended by linearity to an action of the off algebra Fg on A, making A an Fg module algebra as well. So we can form the smash product, and in this case, the multiplication is just given by the following simple rule. In particular, if G is a group acting by automorphisms on Lie algebra, then this action can be naturally extended to an action on the universal enveloping algebra of L. And so we can form the smash product. In a similar way, we can also consider the smash product of a restricted enveloping algebra and a group algebra Fg when G is a group acting by restricted automorphisms on the restricted Lie algebra L. This kind of smash products frequently arise in the theory of algebras, the interest being motivated by the celebrated theorem of Cartier constant Milnor-Moore, which states that over an algebraically closed field of characteristic 0, a co-commutative of algebra H can be presented as the smash product of a universal enveloping algebra capital UL and a group algebra Fg, where G is a group acting by automorphisms on the Lie algebra L. The conditions under which this mesh product satisfies a polynomial identity were established by Bakhturin and Pedrograski. They showed that given a group G acting by automorphisms on the Lie algebra L over a field of characteristic 0, the smash product of U of L and Fg satisfies a polynomial identity if and only if G contains an abelian normal subgroup A of a finite index. In other words, G is virtually abelian. The Lie algebra L is abelian, and the action of A on L is trivial. In positive characteristic, we have that U of L smash Fg satisfies a polynomial identity if and only if all the following conditions are satisfied. And again, if G is a group acting by automorphisms on a restricted Lie algebra L, then the smash product of the restricted developing algebra of L and the group algebra Fg satisfies a polynomial identity if and only if the following conditions are verified. Now, what specifically identities satisfied by smash products? Of course, as U of L smash Fg contains an isomorphic copy of U of L and an isomorphic copy of Fg, here the hard task is to understand the action of the group G on the Lie algebra L. In collaboration with Hamid Sethi, we showed the following results. Let's start by solvability. Suppose that the group G is acting by automorphisms on a restricted Lie algebra L defined over a field of odd characteristic. Then U of L smash Fg is insoluble if and only if the commutator subgroup of G is a finite group and L has a finite dimensional P-nilpotent G-stable restricted ideal P such that L modulo P is abelian and the action of G on L modulo P is trivial. The solubility problem characteristic 2 remains unsettled. And here an additional difficulty is that, unlike the odd characteristic case, in characteristic 2, the tensor product of truly solvable associative algebras need not to be Lie-solvable, which makes things much more involved. Let's pass to the nilpotency. Given a group G acting by homomorphisms on a vector space V, we will say that G acts nilpotently on V if there is a chain of G-stable subspaces of V such that the induced action of G on the factors is trivial. Again, if G acts by automorphisms on a restricted algebra L, then U of L smash Fg is Lie-nilpotent if and only if G is nilpotent and its commutator subgroup is of finite group, L is nilpotent, G acts nilpotently on L, and L contains a finite dimensional P-nilpotent G-stable restricted ideal P such that L modulo P is abelian and the action of G on it is trivial. About the ordinary case, we have the following. Suppose that the group G acts by automorphisms on an arbitrary algebra L. Then in zero characteristic, U of L smash of G is resolvable if and only if G and L are both abelian and the action of G is trivial. In odd characteristic, capital U of L smash Fg is resolvable if and only if L is abelian, G prime is a finite group, and the action of G on L is trivial. And finally, in positive characteristic, capital U of L smash of G is Lie-nilpotent if and only if L is abelian, G is nilpotent. The commutator subgroup of G is a finite P group, and the action of G on L is trivial. Now, as an application of the previous result, take a co-commutative of algebra over a field of characteristic 0, and suppose that this of algebra H is Lie-solvable. Then, as resolvability is preserved by extensions of the ground field, we can assume that the ground field is algebraically closed. Then, by the Cartier-Constant-Milnor-Moore theorem, we have that H is isomorphic as an algebra to the smash product of a universal enveloping algebra and a group algebra. So our result applies. And the conclusion is that H is isomorphic to the tensor product of two commutative associative algebras, and so is itself commutative. So by summarizing, if H is a co-commutative of algebra over a field of characteristic 0, then H is resolvable if and only if it's commutative. In the previous result, the hypothesis of co-commutativity cannot be dropped. For a counterexample, consider, for instance, the four-dimensional Swidlers of algebra over a field of characteristic 0 with the multiplication, coalgebra structure, and antipode defined as you see in the slide. Then by explicit computation, one can see that H is Lie-solvable, indeed limit abelian, but of course, H is not commutative. Now I want to say something about Poisson algebras. I recall that a Poisson algebra is a commutative associative algebra over a field endowed with a bracket making the algebra as well, and such that the two operations are related by the Leibniz rule. In other words, the Poisson bracket is an associative algebra derivation. Maybe the most common example of the Poisson algebra is given by the algebra of smooth functions on R to N with respect to the usual multiplication and the classical Poisson bracket. In the same vein, a polynomial algebra in 2m indeterminates over any field f becomes a Poisson algebra with respect to the Poisson bracket defined in the following way, and the resulting structure is called the Hamiltonian Poisson algebra in 2m indeterminates over the field f. Now, take the algebra L and consider its symmetric algebra capital S of L, which is isomorphic to the graded algebra associated to the universal enveloping algebra of L with respect to the natural illustration by the Poincaré-Birkhoff-Witt theorem. And identify capital S of L with the polynomial algebra in the indeterminates xi, where the elements xi are an F basis of L. Then the Lie bracket of L can be uniquely extended by linearity and the Leibniz rule to a Poisson bracket of the symmetric algebra capital S of L. So S of L becomes a Poisson algebra called the symmetric Poisson algebra of the Lie algebra L. Moreover, if the ground field is positive characteristic P, then the Poisson bracket of S of L naturally induced a Poisson bracket on the quotient of capital S of L modulo the ideal generated by the elements x to the p. So in this case, instead of polynomials, we have truncated polynomials. And the resulting structure is called the truncated symmetric Poisson algebra of L. The definition of a Poisson algebra satisfying a Poisson identity is standard. Identities being a non-zero elements in the free Poisson algebra of countable rank. The study of identities in symmetric Poisson algebras started with some results, with some papers by Farkas, Shestakov, and Constant. In particular, Farkas proved that in characteristic 0, capital S of L satisfies a Poisson identity if and only if L contains an abelian subalgebra of a finite codimension. Some years later, Gianbruno and Pedrograski extended the Farkas result in arbitrary characteristic, and moreover, determined the conditions under which the truncated symmetric Poisson algebra of a restricted Lie algebra satisfies a multilinear Poisson identity. Precisely, given a restricted Lie algebra L, then its truncated symmetric Poisson algebra satisfies a multilinear Poisson identity if and only if there is a restricted ideal H of L such that L modulo H and H prime are both finite dimensional, and H is an nilpotent of the class 2. But Some years later, more recently, Montero Alves and Petrograschi put the focus on Lie identities satisfied by symmetric and truncated symmetric Poisson algebras. Let me first introduce some terminology. We will say that a Poisson algebra P is nilpotent to mean that P is nilpotent as an algebra. Moreover, we will consider the chain of Poisson ideals of P defined recursively by P to 1 equals P and P to n plus 1 equals the Poisson ideal generated by Pn, P in P. We will say that P is strongly linear-potent if this chain vanishes after a finite number of steps. And in this case, the minimum n such that Pn plus 1 is 0 is called the strong linear-potency class of P. Clearly, strong linear-potency implies linear-potency, but the converse is false in general. However, Montero Alves and Petrograschi proved that for truncated symmetric Poisson algebras, linear potence and strong linear potence are indeed equivalent properties, which occur exactly when L is nilpotent and its derivative subalgebra is finite dimensional. Furthermore, if the ground field has characteristic greater than 3, then the linear potency class and the strong linear potency class of S of L coincide, and it's given by the following formula. The possible equality of the linear potency and the strong linear potency class in characteristic 2 and 3 remains an open question. And of course, in this case, this number only represents an upper bound for the linear potency class of S of L. Now let's consider solvability. We will say that the Poisson algebra P is solvable if it's solvable as a Lie algebra. Moreover, we will consider the chain of Poisson ideals defined by delta 0 P equals P, and for every positive integer n, delta n P equals the Poisson ideal generated by the commutators of delta n minus, yes, the commutators of delta n minus P in P. We will say that P is strongly solvable if delta n P is 0 for some n sufficiently large. And in this case, the minimal n with this property is called the strong derived length of the Poisson algebra P. Also in this case, strong solvability forces solvability, but the converse is in general not true. Montero Alves and Petrograschi proved that if the ground field has characteristic different from 2, then S of L is solvable if and only if it's strongly solvable. And this happens exactly when L is solvable and its derived subalgebra is finite dimensional. This fails in characteristic 2, and in this case, solvability is in fact a strictly weaker condition than strong solvability. The same authors proved that given an arbitrary Lie algebra L, its symmetric Poisson algebra is linear potent, strongly linear potent, or strongly solvable, if and only if L is abelian, so in the trivial case. And the same conclusion is true for solvability, provided, again, that the ground has characteristic different from 2. Okay, again, in characteristic, this is false in characteristic 2, and as a matter of fact, the complete characterization of resolvable symmetric and truncated symmetric Poisson algebras was left by the authors as an open problem. In this respect, in their paper, they proposed the following conjecture. Suppose that the algebra L is defined over a field of a characteristic 2. Then the symmetric Poisson algebra of L is solvable if and only if L splits in the direct sum of a one-dimensional subalgebra and an abelian ideal A, such that the adjoint map of X algebraic only on A. However, I proved that this is not necessarily the case. In fact, take L algebra L over a field of characteristic 2, and suppose that L is an nilpotent of class 2, and that the center has codimension 3 in L. Then S of L is solvable of the derived length exactly 3. So this disproves the previous conjecture. For a concrete example, consider, for instance, the relatively free nilpotent Lie algebra of class 2 on 3 generators over a field of characteristic 2. Then this Lie algebra does not contain any abelian ideal of a dimension 1, but in this case, S of L is solvable in view of the previous result. Now, in what follows, I will consider the identities of arbitrary Poisson algebras and then apply these results to prove a corrected version of the previous conjecture and to generalize the aforementioned theorem by Montero Alves and Petrograsky about the solvability of S of L to all reduced Poisson algebras. We start with the following result, which represents the Poisson analog of the corresponding theorem by Jennings. If the Poisson algebra P is strongly solvable, then the Poisson ideal generated by the derived subalgebra of P is associative and nilpotent of index bounded by 2n minus 1, where n denotes the strongly derived length of P. Furthermore, P is strongly nilpotent if and only if P is both nilpotent and strongly solvable. An important result for resolvable varieties of associative algebras is represented by the following theorem, proved by Smirnov and Zalewski and independently by Sharma and Srivastava. They proved that if R is a resolvable ring, then the ideal generated by the elements of this form is nilpotent of index bounded by a function of T. A Poisson analog of this result has been obtained in collaboration with Usefi, where we proved that if the Poisson algebra P is solvable, then the Poisson ideal generated by the elements of this form is associative nilpotent of index bounded by a function of the derived length of P. Now, it follows from a theorem by Mishenko, Petrograsky, and Zaitsev that in characteristic 0, if a Poisson algebra is solvable, then the commutators are nilpotent. In the first statement of the next theorem, we extended this property in any characteristic different from 2. In characteristic 2, the result is not valid. Moreover, if P is soluble and the characteristic is greater than 2, then the Poisson ideal generated by the commutators of P is nil of a bounded index. And the same conclusion is true for linear potency over any field of positive characteristic. Okay, we will say that Poisson algebra P is reduced if it's reduced as an associative algebra. In other words, if P does not contain any nilpotent non-zero element. As an immediate consequence of the previous result, we have that if P is reduced, then P is nilpotent or strongly soluble only when P is abelian. And the same conclusion is true for solvability, provided that the ground field has characteristic different from 2. In particular, as symmetric Poisson algebras are domains, they are reduced. So as a consequence of this corollary, we have the theorem by Montero Alves and Perogradsky about solvability of S of L that I showed you before. Moreover, another application of our previous results allows to settle the solvability problem for symmetric and truncated symmetric Poisson algebras in characteristic 2, thereby completing the classification. This has been accomplished in a joint paper with Usefi, recently appeared in the Bulletin of the London Mathematical Society. We proved that if L is defined over a field of characteristic 2, then its symmetric Poisson algebra is solvable if and only if either L splits in the direct sum of a one-dimensional subalgebra and an abelian ideal A such that this condition on the joint map of X is verified, or L is nilpotent of class 2 and the center of L has codimension T in L, or again, L is a central extension of a certain three-dimensional Lie algebra. Finally, for the truncated case, we have the following. Suppose that L is defined over a field of characteristic 2, then its truncated symmetric Poisson algebra is solvable if and only if L has a finite dimensional solvable ideal I such that L modulo I splits in the direct sum of a one-dimensional subalgebra and an abelian ideal A such that the following condition on the adjoint map of X is satisfied. So the last two results prove a corrected version of the conjecture that I showed before. Okay, this is more or less what I wanted to say. I can stop here. Thank you for your attention.
So let's thank the speaker. Are there any questions or comments?
There is a question in the chat.
Hi, Jose.
Oh, sorry.
Hi, Salvatore.
Do you have a question?
No, but there is one in the chat.
Yeah.
Okay, okay.
So it's better you read it. It's a little bit long.
Is there any question in the chat or no? Oh.
Professor,
Yes,
Professor
there is
Siciliano,
some...
I am the one who wrote the question. Good morning.
Hi, okay.
My question is, I'm dealing with some non-associative algebras. And the question is there some way to prove that they are PI or not PI? My guess is they are not PI, but I don't know how to prove it. Any idea? Thank you.
I did not check in this direction, but yeah. It's,
do you know any reference, any good reference for a non-associative case?
For non-associative case,
these algebras behave differently than alternative and Jordan. They are not alternative, they are not Jordan, because they are not power associative.
I don't have a reference, but I can see if there's something in the literature, and then I can contact you by email. I don't have a reference about this kind of products. Okay.
Thanks, I appreciate. Thanks.
Thanks.
Thank you.
Maybe nobody considered this kind of problem. I will see if there is something in the literature, and in case I will contact you by mail.
Okay,
any other
more questions?
Yeah, maybe. Okay.
More questions or comments? So let's think. Oh, okay.
It could be interesting to see what are the results among those you mentioned could be generalized to Skleanin algebras. Skleanin algebras, they could be considered as a generalization of Poisson algebras.
Yeah. This is a very good.
I will write you details later.
Thank you very much. This is a very interesting question for future research. Yeah.
More questions? Comments? So let's thank the speaker again.